afternoon, everyone. First of all, I would like to thank you, the SPT organizers, for inviting me the second time. And also, I'd like to thank Kaggle to sponsorship for the travel. And I would like to say it's an honor to be here again. And today, I will talk about automated machine learning. It's a topic of my personal interest and also is part of my daily work on Apple. So what is automated machine learning, or autoML? There are many definitions. I have my personal definition, but the first one is the Wikipedia definition. It's very simple. It's the process of automating the end-to-end, the process of applying machine learning in the real-world problems. It's a very broad definition, but I like the second and the third one. Definition that I put on the slide is an intuitive tool that enables anyone to do machine learning, and also is a productive tool for a data scientist. So I'm telling here that is a tool not only for data science, but everyone. And the last one, autoML, is an AI that builds AI. This is the simplest one. So automated machine learning, in theory, is pretty simple. If you take that macro vision of the process. But if you look inside the black box of what is automated machine learning, the process becomes very complex, right? But the idea is to abstract that complexity into a tool that enables anyone to do machine learning. So basically, autoML, the blue rectangle on the middle of the screen, just need one input that is a data set, right? A data set with labeled data. So this is the basic prerequisite of the autoML, having the data set, right? But once you have it, the idea is throw that data set to the autoML and let autoML solve your problem. autoML, you analyze the data, autoML, you build features, you extract some statistical information about the data set, you build models for you automatically, tune hyperparameters, ensemble models, provide some visualization of how the model works, and then the output is one model, one simple model, right? That you can use that model to have a prediction, a guess on the new data. It's taking a look at the picture. You see the green model on the output of the autoML. So it's just a matter of input new data to the model and get the reward, the prediction, right? So why autoML? Why use it? I built some slides trying to explain why it's important to use autoML. So according to Forbes, the world generates a lot of data per day. It's 2.5 zettabytes, and it's growing exponentially, right? It's a lot of data. So imagine how to process that amount of data using like manual tools and human manually trying to analyze the data, doing some ADAs, trying to fit models on that amount of data every day. So autoML is a tool that can automate it, right? Process large amount of data in a reasonable time. Why autoML? Okay, another reason is the growing of the data science job, right? So everyone knows that there's a growth in the last years in the demand for data science. But actually, this demand of data scientists is effect of the amount of data we have from the previous slide, right? All the companies, everyone in the world knows that there are a lot of data that need to be explored, and that grows the demand, right? And the growth is very high also. Some LinkedIn surveys is showing from 6 to 12 times the growth in the past 3 years. This is another reason. This is another survey also from LinkedIn, but showing numbers. from 2015 and 2018, we can see in some cases a growing demand of more than 100 times. Okay, some technical stuff. Why AutoML, right? Again, I made some small experiments. I use 50 different data sets, all binary classification data sets, and I fitted 5 different training algorithms on that data set, right? And what is the experiment? I fitted first using the default hyperparameters for all these algorithms on the 50 data sets, and the output is the mean average of the performance of that 50 data sets training on default hyperparameters, right? Then I tuned the hyperparameters individually for each one of the 50 data sets, and also I present the new performance after tuning the hyperparameters. And we can see in the final results that there's a gain of almost 5% in the overall performance accuracy of the models when we tune the hyperparameters. And this is one of the reasons to use autoML. autoML can tune the hyperparameters automatically for you, right? And usually autoML use the state-of-the-art algorithms to do that kind of hyperparameter tuning. Another reason to use ensembling. autoML can build several hundreds, thousands of models for you automatically. autoML works building a lot of experiments. Each model from the beginning to the end can be considered one experiment. And once you have hundreds, thousands of experiments, how to combine that models in order to improve the accuracy of the final model, the final solution, right? autoML can do automatically for you. Doesn't matter if it's a simple weighted average or a complex stacking of the model AutoFold predictions. Doesn't matter. If autoML is going to choose 5 of the 1,000 models it was built, autoML do it automatically for you, right? This is another reason to do autoML. And it's proving that ensembling models, we can improve even more the accuracy of the final solution. Model interpretability is a hot topic right now. It's about understanding how the model is predicting, right? Why the model takes that decision on predicting something using the information fitted, right? So this is very important when you try to defend or you try to explain for someone that doesn't know data science why your model works. It's very important on the daily basis, right? Not only for experiment data scientists, but for the general user of a tool like autoML. This is one example on the picture. Why that model, the forecasting weather model predicted 775 degrees, right? Maybe there's like an explanation, maybe there's a bug in the software, but maybe there's something wrong with the model. Okay, the autoML have a life cycle. It's similar to a machine learning life cycle. And basically one experiment in an autoML can be defined on that 5 circles, right? First one is the top one, the orange one, is when you grab the data. You have a problem, you define a problem, right? Then you grab the data and you annotate or you have the labels, the ground truth, the answer for the examples that you have, right? This is the first step. Then, based on that, you go to the gray circle. You need to join the tables, clean the data, input the data, prepare the data for the training algorithms. Then you need to analyze the data sets, build the features, maybe process some feature selection on the data set. Then after that step, you can train an algorithm, maybe choose some best algorithms to train for that specific data set, choose a validation strategy, process some hyperparameters optimizations after the model was fit. After that, you deploy the model, you can score a new test set, analyze the results, and you are ready to start the cycle again, right? This is basically one experiment in a machine learning environment and one experiment for an autoML system. But this is the very basic macro vision of machine learning lifecycle. Okay, the first step is defining a problem, right? That specific step is not part of autoML because defining a problem is something, it's a demand for each person or company, right? Is defining a problem. This is the first problem when building any machine learning solution. And usually some people think it's the hardest problem is to define a problem to solve, right? And I've seen it's very hard in the real life. Define the problem correctly, right? Then gathering the data, choosing the right database to store the data, if it's going to be a big data or not, you need Spark or some other form to process the data, is all in this step. So it's not necessarily automated ML yet. Automated ML starts here on data preparation and wrangling, right? So it's how you're going to load the data, to join the tables, clean or drop values and errors in the data set, remove outliers, sometimes it's necessary, process some data augmentation or different data sampling. This is all steps of automated machine learning process, right? And usually the automate decide which of these steps needs to be done or not. Analyze the data. This is the next step. So feature type detection, feature distribution, correlations between features, clusterings, feature engineering. All these steps can be automated using autoML. Then training a model, choose the range of algorithms. What are the algorithms that we can use to fit that specific data set, right? Usually, just looking at the data set is possible. Just look at the data set or the problem, is possible to define a range of training algorithms to be used. And autoML do it for you. Choose the validation strategy. This is a very important point. autoML can define if the data set can be validate using a simple cross-validation, using random k-folds to be evaluated, or if there's some temporal dependence on the data set and a temporal validation must be done, or maybe some of the rows or IDs of the data set must be grouped in order to be in the same fold on the validation. So this is all the steps of autoML, and this is very important. Hyperparameter tuning, architecture research, especially for neural networks, feature selection, and finally ensemble, right? Then next step, autoML can test a model, analyze predictions, check for inconsistency in the predictions, calculate the relevant metrics. More than one metric can be used to evaluate the performance of the autoML solution. Compare model predictions, try to define if the models are very high correlated or there's some diversity between the predictions, and use it in favor to improve the accuracy, and a new round of the autoML process, and prepare the model for interpretability, right? So the last step, autoML also can deploy a model in production. This is very important. Some companies think it's very hard to deploy a model in a form that can be used easily in the future, right? But autoML can deploy a model, can check for consistency of the results, can prepare for the maintainability, like versioning and taking care of the model to be every time health in the system. Also can check for data health, right? Data can be messed, the wrangling and the processing, and the autoML can check if the data is okay to be used in the autoML system. Okay, this is a very quick vision of the autoML, just to have an idea what we need to expect from the autoML. But what are the still challenges for the autoML, right? Imagine you see that table with 4 columns, right? And you are using your human intuition to try to analyze that table. On the first column, you will see there's a free text, right? There are 3 different values. This is a test, I like data, ask a DS about data. So using human intuition, I believe this is a free text column. The second one are just numbers. The second column are just numbers. The third column are random numbers. And the last column, we see 1,80, 5-6, 1.55, 2.05. So what can be that column, right? Maybe it's a free text, maybe it's not. But it's, at this point, it's hard to know what it is. But if I put the name of each column, we can start to use the human intuition to try to define what is each variable here on that table, right? For example, the first column is a categorical feature. Actually, it's not text. Next is not free text. It can be a categorical feature, right? But we know because it's written on the header, on the name of that variable, right? The second one is zip codes, right? First, we thought it's just random numbers, but now we know it's zip code. Zip codes must be treated different than just a numerical variable, right? We are using human intuition to know that. The third one is timestamp. It's a date and time feature, right? Date and time feature needs to be processed differently than just a numerical feature. And the last one, human height, right? But the last one, there's a problem. There are different characters defining the numbers. For example, there are comma, there are point, and there are inclusive different units. 5-6 probably is 5 feet, 6 inches, and it's mixed with meters on the other values, right? So it's possible to use human intuition to define, to look at that and have that insight about the data. But imagine this is a big challenge for the machine to do what we made here, just looking at the header, the name of the features, right? This is one of the challenges of autoML. Also, automatic feature discovery, we can discover the distribution associated with each numerical feature. Machine can do it automatically. Try to find if any numerical feature have more than one distribution mixed, or maybe it's a combination of multiple features, multiple variables. Another challenge is automated feature engineering. I used to say that feature engineering is like an art, and usually humans do feature engineering much better than machines, right? And it's true. Feature engineering is an art, and you need to use intuition and creativity to build the new features. So in autoML, the biggest challenge is to try to mimic that human intuition in order to create many new features using the provided features in the data set, right? Why create more features? Because creating more features make easier the job of the machine to extract information from the data set. AutoML can be used for NLP also, but there are a lot of challenges to do AutoML in NLP. For example, you can detect the language, find the language-specific relations between the words. How to clean the text can be different depending on the source of the text. Find misspellings in different languages. You can try like traditional approach like n-gram, TF, IDF, bag of words, extract embeddings using pre-trained models. So there are a lot of approaches for NLP also. And image classification also. There's some automated ML for images also. And it's the same challenge, how to extract information from the feature, how to pre-process each image, how to augment the data for when you're working with images. All of these are challenges for an AutoML system. And the ultimate challenge for feature engineering, how to combine like a tabular, NLP, and image data set in only one data set to solve one problem, combine the three approaches, right? Automate model fit is another challenge for AutoML. So setting a validation strategy, I talked before. Set a relevant metric also is important because a relevant metric can define the final accuracy of the model, or sometimes we're interested in optimize some specific metric. Train a model. I also talked before, if you're going to use a linear decision tree, deep learning, in how to process the data set to use each one of these tools, right? And the last for automatic model fit, optimize hyperparameters for tabular data and classical training algorithms, or neural network architecture search. Just to have an idea for a light GBM algorithm to train, I took a look at the parameters page on the internet, and I counted around 60 hyperparameters to tune just for that algorithm. That algorithm is very complex, but how to tune 60 hyperparameters to improve the accuracy, the performance of the model to the top? This is a challenge. The same for neural network, but neural network, there are hyperparameters and there are neural network architecture at the same time. So for hyperparameter optimization, there are several algorithms. Some classical algorithms like grid search and random search have been using for 2 decades. But the state of the art is based on Bayesian optimization right now. Just a quick view of the grid search and the random search. Grid search is when we define a combination of hyperparameters. There's a very well-defined combination of hyperparameters, and the model tries to fit for each combination of that hyperparameters. For the random search, the algorithm chose randomly the hyperparameters and built different experiments, trying each time a random set of hyperparameters, right? Just a quick example of the grid search and the random search. The advantage of grid and random search is that the experiments can be parallelized. So, for example, if you have 30 cars available, you can run 30 experiments in parallel. But for the Bayesian optimization, it's a serial algorithm, so it needs the previous step to run the next step. So it cannot be parallelized, but in theory, the Bayesian optimization converges faster than the previous ones. And finally, ensembling also it's a challenge for the AutoML because, as I said before, ensembling you can combine multiple models in only one solution. And the challenge is choosing the right models to combine and how to combine that models together in order to increase the final accuracy, the final performance of the model. There are a lot of variables in that kind of algorithm, including the training strategy that's going to be used. And the last one, model interpretability, right? I told before, but understanding the model is very, very important. It's a matter of trust in your model, because how can you trust in a black box that just predicts something for you, right? Understanding the model can increase that trust in the model and make it easier to implement in a real-world problem, to solve a real-world problem. Model interpretability is very easy for a linear regression. You just need to look at the coefficients. But as the algorithm starts to grow more complex, the interpretability starts to become harder to build and to understand. And imagine AutoML that ensemble a lot of models, it becomes even harder to interpret the model. This is one classical example of one model interpretability library in Python. That model tried to detect husks and wolves in images. And in that example, that husk was identified as a wolf, right? It's wrongly identified as a wolf. And then using model interpretability on the picture on the right, it shows what part of the picture was used to detect that husk as a wolf. And it showed that only the snow that's around the dog was used to detect as a wolf. And why it happened? Because all the wolf images using the training set are pictures taken from wolves with snow background, right? So the models learn how to detect snow and not the animal, right? And the model interpretability helped to discover that issue with the model, and we have time to fix it. Another challenge, cost and model performance versus time, right? We can use our entire life to train a model and build infinite number of experiments, but the cost associated with the training is linear increasing, right? But usually the performance of the model tends to become flat after some point. So detecting that point of cost and time and performance is another challenge for the autoML. Another challenge, big data, scalability, specifically if you need to estimate if your data needs a large amount of RAM to be processed, or you need a clustering to be processed. Maintainability is another challenge, and last one, interpretability, right? So the advantage of autoML, in my viewpoint, is near to zero complexity for the users. AutoML is to everyone, not only experts, right? Reduce costs of hiring ML experts, anyone can use, including the ML experts, to make the life easier and more productive. Reduce human bias and errors, because they're not using any human intuition or bias to build the models or tune the hyperparameters. Increase the productivity, fast insights about data and performance. You need to know how your data set will behave. AutoML, it's a good tool to help you to know how the data set behaves. You be sure that you're using state-of-the-art in the ML, right? You're running AutoML algorithm, you'll be sure that some of the models are being trained using the state-of-the-art that we have right now. Is scalable and is deployed. That are all the main advantages in my viewpoint for AutoML. And that's it. Thank you again.